I will start. Yeah.
Okay, so our next speaker is Alessandro Podo from France, and he's going to talk about microcausality in Lorentz-breaking backgrounds. So maybe I will send you a reminder when 5 minutes are left. Hello?
Thanks.
Hi.
Yeah, thanks very much. It's a great pleasure to be able to give this talk in this. Can you hear me? Can you hear me? Hello?
Yes.
Hello?
Yes, we can hear
okay?
you, but
It's
there
working
is
now?
some disturbance.
Okay, yeah, I'm sorry about it. It's the internet connection. Maybe it's not optimal. Let me know if there are issues along the way. But yeah, as I was saying, it's a great pleasure to be able to give this talk in this online seminar series. So what I want to tell you about is some work that we published the last few months with some collaborators from Columbia University. And the topic is microcausality and Lorentz-breaking backgrounds. So the motivations comes from so the topic will be a bit talk, but I will be able to convey all the information. But the main thing I want to interrupt me on points and ask me questions if something clear. So just to start, let's give some motivation. So why do we care about this? So in flat space, we know and understand quite well, not perfectly, but quite well, the properties, the analytic properties of scattering amplitudes. And this has been used to derive positivity bounds on effective field theory coming from consistency conditions. This has been very influential, both from a theoretical point of view. It has been used in important physical works, such as the proof of the A theorem.
Sorry,
And
Alessandro.
also
Probably you can switch off the camera because the connection is quite unstable.
Yes.
Loud
Voice is breaking.
Yes. Yeah, hopefully it's better now. Let me know if it's still not good.
Yeah, let's try.
Yeah. So as I was saying, positivity bounds for scattering amplitudes have been very interesting and useful in many different contexts. So it would be nice to have some tools to extend this kind of considerations beyond the flat space case. And this will be very interesting for a number of reasons. First of all, it can have applications to topics of interest for high energy and gravitational physics, such as early universe cosmology or the physics of black holes. It also can be interesting for the study of finite density phases of matter, especially in a relativistic context, and can have applications in superfluids, fluids, Fermi liquid theory, and more. One kind of target that it would be nice to address is to try and constrain the dynamics of the inflaton, which is the putative field that has driven the very early phases of exponential expansion of the universe. And in particular, inflation is very successful at explaining some of the features of primordial fluctuations, but we have a very poor understanding of its dynamics. So can we constrain the interaction of the inflaton using the first principles? And can we maybe first test these first principles in such a high energy regime? So with this motivation, what I will do is I will consider theories that are in a Lorentz-breaking state but in which the Hamiltonian itself, so the dynamics, is Lorentz invariant. So I'm not considering theories that break fundamentally Lorentz invariance, but only theories that are in a state that is Lorentz-breaking. And so the first thing one might hope to do is to kind of generalize the amplitude problem to this context. However, this can be due to several different reasons. One reason is that the space-time can have a very different asymptotic structure from that of Minkowski space. So it's not clear how to define asymptotic states and how to define a scattering amplitude to begin with. It's often the case in generic spacetime that there is no time-like Killing vector, so there is no preferred vacuum state, no preferred Hamiltonian, and it's not clear how to define time evolution. Even when these problems are not there, as I'll show you in a second, it often happens when you are in Lorentz-breaking states that the asymptotic states are not there are not stable single particle asymptotic states. This might be due to the fact that the excitations are unstable. So this is very familiar in condensed matter physics. Usually excitations of condensed matter states are quasi-particles. So these are single particle excitations, but they are well-defined only at low energy because they decay. And their decay rate will depend on energy, but strictly speaking, they will not be well-defined perturbatively. So these are some issues that one encounter. And even when these issues are not present, giving up Lorentz invariance complicates a lot the structure of scattering amplitudes, as I will show you in the next slide. So the first thing I did with my collaborators was to try to forget about these issues for a second, work perturbatively in the simplest example you might imagine, where these issues are kind of secondary, and try to look if the amplitude is still has nice properties or not. And what we found is, so what we did is we studied the lambda particle theory, but at finite density. So this gives rise to what is known as a relativistic superfluid. So the finite density is induced by adding a chemical potential, which modifies the ground state of the theory. And then you can look at excitations around this ground state. So there are two classes of excitations. One is known as phonons. The other one, phonons are the analog of Goldstone bosons, but for this finite density phase. And then there is a radial mode, and then you can scatter phonons in this theory. And since you have the UV completion, you can consider the scattering amplitude, say at free level, but at arbitrary energies, and see what is its analytic structure. And what we found is that even working at free level, there are very unusual features. In particular, the amplitude as a branch cut. If you use Mandelstam variable parameterization, you work in the forward limit, so t equals 0 in some center of mass configuration. You find that the amplitude has a very complicated form that I'm not showing, but in particular as a branch cut of the square root type on the negative s-axis. And this is very unusual because usually, first of all, relativistic amplitudes are crossing symmetric, and this is not. But also relativistic amplitudes have branch cut dictated by unitarity, whereas this branch cut is not dictated by unitarity because it only lies on a physical region of the values for the S Mandelstam invariant. So the analytic structure is very complicated, and even though the low energy expansion of the amplitude shows some interesting positivity features, we cannot use the usual arguments to understand those, okay? So this is kind of surprising because usually we are used to the statement that causality in relativistic theories implies analyticity. In particular, for scattering amplitudes, causality is the tool that is used to prove analyticity of scattering amplitudes. In flat space, in Lorentz invariant theories. So what about this implication? What happens in this context? So what I want to show you is how causality still implies strong analyticity properties, but not for the scattering amplitude itself, but for correlation functions. And in particular, I will argue that there is a particularly useful representation of correlation functions where analyticity properties are particularly nice and manifest. Before doing that, let me remind everyone what the different statements of causality are, and so that just so that we are on the same page. So causality usually in a non-relativistic context, so in classical, if you want, quantum mechanics or even classical physics, is the statement that only past events can affect the state of the system. And if we consider some response function to some perturbation inserted at time 0, and if we go to Fourier transform, this causality property implies that the response function in omega space is analytic in the upper half plane. And if one assumes further that this response function is well behaved at infinity, for instance, goes to 0 at infinity, one can use these analytic properties to write down dispersion relations. This is, for instance, the very simple example of a Kramer-Schrödinger dispersion relation, which has been extremely useful also in applications in classical electrodynamics. So let me stress that this version of causality does not assume a finite propagation speed for signals, so holds even if signals propagate instantly. Okay. Now, in relativistic systems, we have an extra fact, which is the fact that signals propagate at most the speed of light. And so causality becomes a more stringent statement. Relativity that took place in the past light cone of an observer can affect the state of a system. Okay, so this is a stronger version of causality. And using this, one can derive, assuming again some well-behaved soft behavior of a response function in frequency space, one can still derive some stronger version of a Kramer-Schrödinger dispersion relation. This has been studied in this recent paper by Senatore, Criminelli, and collaborators. And this can also be used in applications in electrodynamics. But what I want to consider instead is a different way to implement causality, which is related to these notions, but it's the way we phrase it in quantum field theory. And this is known as microcausality, and this takes the form of the following statement. So taken two, let's say, scalar local operators, then if we put the two operators at space-like separated points, the two operators commute. So this means that the commutator of these two operators is exactly 0 whenever their distance is space-like. So this is a very strong statement. First of all, let me remark that this statement holds at the operator level. So O1 and O2 are operators, and then we can insert this identity in any correlation function. And in particular, we can insert it in an arbitrary states. So this, being an operator statement, will be valid on arbitrary states. And we can also insert additional operators in the correlator. Okay. And also, this is a non-perturbative statement. In fact, in some formal axiomatizations of quantum field theory, it's taken as one of the foundational axioms of relativistic quantum field theories. So I will use this notion of causality and see what consequences we can get from these once we compute correlation functions in Lorentz-breaking states. Okay. Is everything clear for now, or are there questions?
I don't see any questions here.
Okay. Okay, cool. Okay, good. So as I was saying, we can use this statement also in Lorentz-breaking state. And for definiteness, I will mainly consider commutator correlation functions or retarded correlation functions. So the definition of retarded here assumes that the product of this step function with the commutator is well defined, but in general one can consider retarded correlators, and they will have the same properties as the commutator, because they will always vanish whenever the 2 points are space-like separated. So I will consider either retarded or commutator correlation functions, and the state in which we evaluate this commutator will be some states that I will specify in any example I will discuss, but it can be a finite density state or a curved spacetime. Now, what is this? Well, let me try to derive some consequences from this statement, and then let me tell you what kind of representation might be useful to extract properties from this commutator. So if we consider states in which boosts are can be defined. So all these cases are there is a preferred reference frame, the reference frame in which the system is at boost are broken by the grounds. And for simplicity, I will specialize to the case in which spatial translations and rotations are instead unbroken. So my system is homogeneous and isotropic. But this is mostly a simplification for presentation. The statements generalize. Hello?
Yes, we are not able to hear you. It's getting broken.
Can you hear me?
No.
Hello?
Yes.
Yeah, sorry, I don't know why the connection failed. Can you hear me now?
Yes.
Okay, good. So as I was saying, I will specialize to cases, just for simplicity, to cases in which spatial translations and spatial rotations are unbroken. And this is general enough to include a lot of interesting examples, but it also makes the equations a bit simpler, so I will mostly focus on this. But let me stress that time translations can be broken, and in general, I will also consider examples where they are broken, such as in cosmology. So in this class of states where boosts are broken, it's kind of natural to treat differently space and time. And so what I will do is I will fix, I will consider fixed insertion points in time for a second. And I will look at this object, at this correlator, as a function of the spatial points, insertion points. So if I look at this object for fixed time, but as a function of space, I will notice that because of microcausality, because of the statement I showed you before, because of this statement, this object is a compact support function for fixed t. And this is just telling you that given a fixed time, only a fixed region, only a compact region can have enough time to transmit signal to the observer. So being a compact support function of distribution more formally, it's a very strong property. And in particular, it implies, thanks to some very well-known mathematical theorem, implies strong analyticity properties to its Fourier transform. So if we take this function for fixed time, but as a function of spatial variables, as I said, this has compact support in some ball, in some compact region. This is true if and only if its Fourier transform with respect to the spatial variable is analytic and exponential bounded. And the analyticity is very strong because it's valid everywhere in the complex plane. So you take this complex k vector, spatial momentum, you complexify it. These functions admits a complex analytic extension. It is analytic everywhere in the complex k plane. And moreover, in this whole plane, there is a bound valid for this function. That is that the absolute value of this function is bounded above by something that grows exponentially with the imaginary part of k, but this is just a linear exponential. And the prefactor of this imaginary part of k tells you about the light cone structure. So it's this prefactor is exactly the compact support of the spatial distribution you started from, and this encodes the light cone that you started from. Okay, so by studying the analyticity and by looking at how this 2-point function behaves in the complex plane, you can kind of understand whether your theory is violating causality or not. Okay. So this will be the main tool I will use, and I want to show you how this is useful. So the main point is that in general, it will be very difficult to compute correlation functions in space in general. Whereas working this mixed representation, for instance, in cosmology, is more achievable, is easier to do, and also these representations have this very nice analyticity property that can be useful and can be exploited. Okay, but let me show you that this is valid, at least in some examples we know and love. Okay, so the first is the Lorentz invariant. So in this case, that it's causal using this new observable, this mixed representation for the correlation function. So this is probably something you're not familiar. The commutator in this mixed representation takes this explicit form. So this is something you can derive very easily, for instance, in canonical quantization or in whatever way you like. But the point is that this function, even if it's a function of the omega k is the dispersion relation of this scalar particle, even if omega k is a square root function, if you look at the analytic, if you look at the Taylor expansion of this function sine of omega k t over omega k, the expansion is actually an analytic function of omega square, and as a consequence, it's also an analytic function of k square. So the analyticity in k is, and you can also check that the exponential bound is valid thanks to this other property on the right, which is that the imaginary part of this of omega k is always smaller than the imaginary part of this spatial k. So this might look surprising at first. So for the real part, the opposite inequality is valid. So if you take k real, omega k for positive and omega k is always larger than k. But it's a simple fact to check with the elementary algebra that for the imaginary part, this inequality gets inverted. And thanks to this, because I'm setting the speed of light to 1, and we're in space. Okay, so this property that I can argue that they're also satisfied in every relativistic theory, in particular using the Chandler-Lehmann spectral representation, because in this case, I have the 2-point function of the free scalar. And for the free scalar, I just showed that these two properties are valid. So as long as this representation is convergent, I can just use the previous argument to argue for the analyticity and boundedness of these 2 points in general. And from this, we can also see that for stable particles, the right kind of speed that we should care about in this context is the group velocity. the way to see this is that we have this function that, as I showed you, is bounded by the imaginary part of omega times t, and so if we want this to be bounded by imaginary part of k times t, and the prefactor in general will be just the derivative of this d omega k in dk. And in the limits where you take this k to be real, which is what you'll do for stable particles, this becomes just the group velocity. So as long as the group velocity is smaller than 1 for stable particles, microcausality will be satisfied. Okay. So I showed you some properties that derive just from first principles, and they look nice, they look maybe powerful, but are we sure that we can check them within the effective field theory regime of validity? So usually when we do physics, we're always dealing with effective field theories most of the time for, let's say, for practical applications. So it's important to discuss whether this property I derived is something we can check reliably within the effective field theory, or whether it's something that requires the knowledge of the UV completion of the theory. So what I want to argue is that it is meaningful to check this property within the effective field theory in the low energy limits. So first of all, let me talk about analyticity. So analyticity at low momentum, in particular in the limit of zero momentum, is something we can always check in effective field theory. And this is because of non-analyticities in correlators or in amplitudes, so non-analytic terms, are always long distance contributions. And these are always induced by light states. So all the non-analytic terms we can compute within the effective field theory reliably, and we can check whether the correlator is analytic or not. Regarding exponential boundedness, here the check is a bit more tricky. So as I told you, the bound is some exponential bound, but we want to probe this exponential and see. So if we are only allowed to access a finite range of k and t, we might wonder whether our correlator is actually not growing exponentially, but maybe has only some large prefactor, and we cannot make a very good test. But I want to argue that, in fact, we can take the exponent of this exponential to be arbitrarily large within the effective field theory regime of validity. And this is done by taking the momentum to be very small, but the time, so the time difference between the insertion points of the two operators to be very large, in such a way that their product is very large. So both of these limits are taken within the effective field theory regime of validity, and so nothing forbids us from taking a scaling limit in which one goes to infinity faster than the other goes to zero. So this allows us to probe the exponential behavior of the correlator within the effective field theory regime. And using these, for instance, applying it to kind of Lorentz invariant theories, we can argue for the standard positivity bounds on the coefficient of the d5 to the fourth operator in a massless scalar field theory, just using microcausality without relying on unitarity explicitly. Even if by consistency we expect our QFT to be unitary, the point is that we can argue for positivity, or rather for non-negativity, by using only microcausality. And this is done by expanding around a background that is time-dependent, linear in time, and studying fluctuations around this background. And then noticing that the correlation function will violate this exponential bound unless the propagation speed is smaller than 1, which is true if and only if alpha is non-negative. Okay, so these are some standard kind of tools. Now I want to show you that this property holds also for more interesting examples of theories that break Lorentz invariance. So the simplest thing we could come up with to check was the 5 to the 4th superfluid, but here we're not taking a low energy limit. We're looking at this theory at arbitrary energies, but at 3 level in the coupling. And I'm putting it at finite chemical potential as I was describing before. So in this case, as I was saying, there are 2 modes. There is a gapless mode that is described by this dispersion relation on the bottom in red, and the gapped mode that is described by this other dispersion relation in blue on the top. So now the 2-point function, say for the operator phi2, so for the real scalar that corresponds to the imaginary part of the complex field, takes this form. So there is a sum over 2 branches. There is 1 branch where you exchange the gapless mode and 1 branch where you exchange the gapped mode. And the dispersion relation in this theory is very complicated. There are double square roots, and the overlap of operators with state is also very complicated. There are again double square roots. So this might look hopeless. How is it possible that this correlation function is analytic in K at fixed T? So even if this looks surprising, in fact, this function is analytic, and we can prove it with the following argument. So you can notice that the dispersion relation omega, this property that omega square is something plus or minus. So A is just something analytic. It's just this K square, kind. And this B is something that includes the square root. So now if you expand, if you look at the Taylor expansion of this sine omega over omega, this only has even powers of omega. So it's an expansion of omega square. But then you are also summing over the 2 branches plus or minus that were corresponding to plus or minus the value of the square root. And so if you look at the Taylor expansion of this, you will notice that this Taylor expansion is even in B. So everything that is odd power of B cancels. And you're only left with even power of B, which are analytic functions. Even if so this means that if we're doing this theory without doing any low energy expansion, we actually need to include both gapless and gapped mode to have a macrocausal theory, which is kind of surprising, but that is what we find. And now you might wonder, well, what about the low energy limits of this? So we might take the low energy limits and which we integrate out the gapped mode from this theory. We integrate it out and we write some effective theory for the low energy mode. So at quadratic order and leading order in derivative, this is described by just this kinetic term. And then we can include the interactions and their derivative. So at 3 level here, the speed of sound is more than 1, but we can compute 1 loop corrections to this 2-point function, include also derivative corrections. And so we find something of this form where this Q is just a polynomial of omega and K. And what we find is that if the dispersion relation, so what we find is that the logarithm always falls, so is always fine as long as the speed of sound is smaller than 1. But on the other hand, the higher derivative corrections can be bounded thanks to the fact that if the dispersion relation takes this form, so it's the leading order plus some correction times K square, so this is an higher derivative correction. We can show that this correlator violates our exponential boundedness unless this coefficient alpha is bounded by the following expression. So it's something that depends on the UV cutoff. And then there is a factor that depends on the sound speed. And as you can see, this factor can become small, for instance, if you take the sound speed close to 1. So this is an interesting bound, and what is also interesting about it is that this bound is non-trivial also when this factor alpha is negative. So in that case, we couldn't use subliminality to constrain this. So if alpha is negative, the correction to this special relation is pushing you in the region where naively you'll say that excitations are subluminal, so everything classically would look okay. But in fact, exponential boundedness is violated if this alpha is taken to be too negative. So this is, I think, something interesting that shows you that microcausality in general is stronger than subliminality. And we can run additional checks that our formalism makes sense. So something we did that we also thought was interesting was looking at the effective field theory for phonons now in a solid. And this is the same as this exotic class of condensed matter systems called as Fremits. So for experts, I am also mentioning those, but let me just talk about solids. So in the case of solids, let's say in 3 spatial dimensions, you have now 3 classes of phonons. You have longitudinal phonons and then two types of transverse phonons. And in general, longitudinal and transverse phonons will have different propagation speeds. So now you can compute the commutator correlation function for this scalar field, the phonons. So by the way, let me notice that in this particular case, I'm giving up. I'm considering operators that are not scalar under rotations. So this object will not be invariant under rotation, but it's something that transforms with 2 indices. And as a consequence, we will have to check analyticity
Hello?
in our...
Hello?
Yes.
Yes, we have 5 minutes left.
Yes. Yes. Okay. Good. Yeah. I will go towards the conclusions. So in this case, we have something that is analytic in vector k rather than k squared. So it's a bit. So it's something to keep in mind. But what is interesting is that individually, the longitudinal and the transverse phonons are not analytic taken alone, because these longitudinal and transverse projectors depend on unit vectors, and these are not analytic combinations of K. But if you include both of them, what happens is that the only terms that will be non-analytic are the leading terms in the Taylor expansions of these signs, and those cancels between longitudinal and transverse. And so you end up with something that is actually analytic in vector K. So again, the criterion we have works. It's just a bit interesting to see how things work out, but maybe it's not surprising that at the end of the day, longitudinal and transverse field taken in isolations are not local, because the way you define them, if you want, the projection you do is a non-local statement. Okay, so we checked the same also in the case of hydrodynamics. I don't have the time to discuss it, but you can ask me if you're interested. The last point I want to touch upon is the fact that we have we can apply also these ideas to the case of scalar fields, for instance, in some expanding backgrounds. And the case we looked at was a scalar field, let's say an inflaton, in slow roll FRW background. So I'm skipping a lot of details, but you can write the action for the curvature perturbations. So this is written what is sometimes called comoving gauge. So zeta are the curvature perturbations. And then you can look at the correlation functions for the zeta. But now, naturally, we will be using spatial momentum and time, as I've been using throughout the talk. And the mode functions now will be a bit more complicated. So there are some special functions known as Hankel functions. And we can check whether our properties are valid or not. The important point is that differently from what we usually do in cosmology, we're not looking at correlators. So if we compute this commutator, kind of magically again, the properties, the analytic properties of the Hankel functions work out in such a way that this combination is analytic. But this combination is analytic only if you take this very special combination, imaginary part of zeta times zeta star. The way this works out is that the Bessel functions, so Hankel functions are related to Bessel functions, and Bessel functions are not analytic, but they have a prefactor that depends on some index, which makes them non-analytic, times an analytic function. And this prefactor cancels between the two zeta and zeta star, because this gives rise to some j of minus nu times j of nu. And this cancel the non-analytic terms. So the validity is satisfied. And we can check that using these, we can then look at the exponential boundedness. And this will be satisfied only if the sound speed of the curvature perturbation is smaller than 1, which is not surprising. But this sense is more or less a rigorous way to argue why this should be true. And if we relate these in terms of some competitions, such as or maybe the theory of inflation operators, this implies that there was some term to extend. Let me conclude since I'm running out of time. I can get some questions if there are. But what I try to argue